So hello everybody, can you hear me?
Yes, we can hear you.
We'll start in 2 minutes. 1 minute. Okay, so in a few seconds, I hope you guys had a good break. Most of you anyway. I know my TAs were working over the break, but I hope the rest of you managed to get some time off. We didn't really have any deadlines or anything urgent over the break, so at least from the ideal end, we tried to make sure that you didn't have any tasks on your head. So before I begin, any questions about everything we've covered so far? Any questions? If not, all right. So we're going to we're going to continue the second half of the course. In the upcoming lectures, we are going to be covering the rest of recurrent networks. We'll cover transformers and then get into generative models. We will have some guest lectures over the coming weeks. And one particular guest lecture that we will have is on November 6th by Omar Khattab, who's now going to be joining MIT as a professor, as an assistant professor. Omar finished his PhD from Stanford and did an amazing dissertation. He was one of the hot candidates on the circuit earlier this year, and we wanted him, but MIT managed to get him, I guess. So he was also an ideal student and an ideal TA. His work is on large language models, and so Omar will be doing a guest lecture on large language models on November 6th. So please be there because he's one of the best. He's a fantastic teacher and he knows the setting. He knows ideal. So you're not going to get a better combination. And he's world famous. All right. So continuing on, here's where we were with recurrent neural networks so far. We saw that recurrent structures are good at modeling time series. So for tasks like predicting the stock market or speech recognition or any similar task where you have to analyze a series of data and then come up with some conclusions, you want recurrent structures like recurrent neural networks. But these models are trained by minimizing the divergence between the sequence of outputs that they produce and the sequence of desired outputs. And so the actual divergence that we define is between two sequences. We compute gradients of this divergence and we train the network through gradient descent and backpropagation. So the main challenge over here is how do you define this divergence? Again, these are time or series analysis tasks. So one such task might be machine translation. Now, when the network produces some output, the output may not be related in any manner with the desired output. It may have a different number of words in the different order, and then you have to somehow define a divergence between the two. And this divergence must be differentiable. And this differentiable divergence must then be used to guide the update of the network parameters. So how do we define this divergence and how do we perform the training? This is the task that we are going to consider over the next 4 lectures. The challenge here is defining the divergence because the inputs and outputs may not be aligned or even synchronous. So Before we get into that, let's just look at the kinds of tasks we can perform with a recurrent neural network. I got some pictures from Andre Karpathy's old page. So here are different kinds of tasks you can perform. This figure to the left is just a simple network where the input goes to a hidden layer, which goes to the output. This is just a regular NLP. There's no recurrence. The kind of networks that we saw earlier and in earlier lectures, where the kind that we saw, that we got seen in the figure to the right. You have a sequence of inputs. Each input is used to compute a hidden state, which is computed not just from the input, but also the hidden state at the previous time. And the hidden state is used to compute the output. So you have as many outputs as you have inputs. This is time synchronous. The outputs are synchronous with the input. This is the kind of network you might use if you want to do part of speech tagging of text, or if you want to predict the stock market on a daily basis. But then you can have other kinds of networks, like this figure to the left, where you analyze the entire input, and once the entire input has been analyzed, you produce an output. So this you would use, for example, if you were performing speech recognition, or if you were performing sentiment analysis of text. And this figure to the right is a little more interesting. Here, the output is a sequence. It's not just a single output like the figure to the left, but the sequence of outputs over here also differs from the sequence of outputs that we saw earlier in this figure. And the difference is that the outputs are not, you don't have one output per input. The outputs are intermittent. So the output has order synchronicity with the input, meaning this portion of the input corresponds to this output. This portion of the input corresponds to this output. This portion of the input corresponds to this output. So if you permuted the inputs over here, the outputs would also change their order. So the order of the outputs is related to the order of inputs, but there is no time synchronicity, meaning the number of outputs is not the same as the number of inputs. And moreover, the spacing between the outputs can be arbitrary. So do you guys understand what I mean by order synchronous, but not time synchronous from this figure? Yes, no, guys, can you just answer with a yes? Because, right. So this, we're going to see. This is what we're going to be focusing on in the next couple of lectures. And then you can have other kinds of models, like this figure to the left. This figure to the left is one where the entire input is analyzed, and then the entire output is generated. So again, there's no one-to-one correspondence between the input and the output. The entire input must be consumed before the output is generated. This is what you would use, for example, if you were performing machine translation. You must analyze the entire input sequence, say a sentence in English, and then generate the entire output, which could be a sentence in, say, French. And unless you've analyzed the entire input, you really don't know what to produce, because the very last word in the input could change the entire meaning of the sentence. So this is a many-to-many model. And then this model to the right is one where a single input generates an entire sequence of outputs. So this you could use, for example, if you were captioning an image. The image would feed in a single input, and out would come the entire caption. So these are all the different kinds of analyses. So Isaac, for the live translation, you would still be using, in live translation, things you get some engineering, but until sentences are complete, you really cannot say what the sentence is. For example, in German, the verb comes at the very end. So you don't know if the guy wants to kiss the other person or punch the other person till the sentence is complete. You obviously cannot begin translating before the last word is in. So you cannot perform the translation in real time. You have to wait for chance. Anyway, continuing on. So let's see how we're going to look at these four models. And today and in the next class. So let's start with the conventional MLP. This, we know how to use it. A single input produces a single output. but it can also be used to analyze a time series. And the way you would do it is that every single input in the time series would be independently analyzed by the MLP to produce an output. And so what this means is that the analysis at time t has no relationship to the analysis at any other time because each input is independently processed. Nevertheless, you can still use this to analyze time series. And in this case, the way you would actually factor in the fact that the input is a time series is through the divergence. The sequence of outputs is going to be compared to a sequence of desired outputs. And so now the divergence over here would be a divergence between two sequences. And that divergence would be used to train the model. So although the model itself is just a straight up MLP, the fact that the model is being used to model time series is somehow brought in through the divergence. It's not a great model for time series, but you can use an MLP to analyze time series in this manner. Even in this setting, a common setting is to say that there is some kind of a one-to-one correspondence desired output and the actual outputs. That simplifies the definition of the divergence. When we have a setting of this kind, this is what we do. We define the divergence between the sequence of outputs and the desired sequence of outputs. And this divergence must be differentiable with respect to the outputs at every single time. This is going to be necessary. So you need to be able to compute the derivative of the divergence with respect to each output yt, namely with respect to each of these outputs. This is essential. And once you can compute this derivative, then you can perform backpropagation. And once again, when you assume a one-to-one correspondence between the output and input, the output sequence and the input sequence, meaning every output in the actual output, the output sequence and the desired output sequence. So meaning that every output in the actual output has a corresponding term in the desired output. Assuming this kind of a one-to-one correspondence gives you the ability to make one further assumption that the divergence between these two sequences can be viewed as the sum of the local divergences at each time, and then computing the derivatives becomes much simpler. So this is when we're using an MLP to analyze time series. Did this make sense? Questions? Give me a yes or no if this made sense to you. Right? Okay. So now here's your first poll, which we will release. Can you guys see the poll? Five seconds, guys. 1, 2, 3, 4, 5. All right, let me end the poll. Here's what most of you thought. And let me ask you. So this first question, true or false? Okay. For some reason, every time I get a chat message on the chat box, I get a little beep here. I hope this is not filtering through over Zoom. Okay. The second question, true or false? Also true, right? Conventional MLPs can be used to model sequences. When we use them to model sequences, the sequence nature is captured through the divergence, right? So, great. Now let's look at the second model, where you have time synchronous outputs corresponding to every input. There's an output, but the model is actually recurrent. So this is what you might use, for example, in predicting stock market on a daily basis, or performing part of speech tagging in text. So every word, the input would be the sequence of words, and every word has a part of speech tag. And the specific tag for any word depends on all the other words in the sentence. So whether this word yellow is a verb or a noun depends on how it is used. So you'd have to look at everything else. So it's a recurrent model, and there's an output corresponding to each input. So here, again, you can have a one-sided network where you process the input left to right and produce one output after each input. Or you could have a two-sided model where you process the input both forward and backward and generate an output at each time. In all cases, regardless of the nature of the network, there's one output corresponding to every input. And this is the key piece, the fact that there's one output corresponding to every input. That's what we are focusing on. My illustrations will show a one-sided network, but pretty much everything that we are talking about here also applies to two-sided networks. So here's how you train the model. You'd be given a sequence of input and output pairs, desired output pairs. So the input would be a sequence. There's going to be a corresponding sequence of outputs by the network. You would compare it to the desired output sequence and then define a divergence. So the divergence is between this sequence and the desired output sequence. And as the first step, this is what you'd use to train the model. So as the first step of backpropagation, you need the derivative of this divergence with respect to each of these outputs. And so the assumption is that this divergence is differentiable with respect to each of these outputs. Once we can compute those derivatives, then you can backpropagate them to train the network. And so again, once you do that, then the backpropagation rules are just as before. Now, again, because you're computing a divergence between two sequences, this can become challenging. And so one common assumption is to, again, assume a one-to-one correspondence between the desired output sequence and the actual output sequence. And furthermore, we will assume that the divergence between these two sequences can be viewed as the sum of the divergences at the individual times. Once you make that assumption, then the sequence divergence becomes just the sum of the divergences at individual times. So the derivative of the sequence divergence with respect to any given output is simply going to be the derivative of the local divergence with respect to the local output. And this can be backpropagated. Is this making sense? Just two of you. What about the rest of you? Okay. And so this is actually a very easy model to deal with. If you have this kind of a divergence where you have one-to-one correspondence and the divergence can be decomposed into the sum of local divergences. And so much of what we do when we train the model is to take, the actual divergence that you will be given may not have this form. And so we are going to twist ourselves into knots and trying to somehow modify that divergence into this form, where the divergence can be viewed as a sum of local divergences, which can be differentiated. And then once we bring it down to this form, we know how to train the model. Again, we'll be seeing more of this in the coming lectures. So here is our second poll. Can you guys see the poll? So Mariam, what was the question again? Why does it not have any sum?
Yeah, the divergence derivatives.
So because so the derivative of the divergence with respect to the output at any time is because the divergence is the sum of many local divergences. Then the subsequent divergences have no direct dependence on this YT, right?
Yeah, but the left side is like y target from time 1 to time t. which become equal
Correct.
to just one time at t, if I don't make
Okay,
mistake.
so let me answer this once the poll is done. We have 5 seconds for the poll. Okay, let me stop the poll, guys. Here's what you all thought. Let me go back and first. Which of these statements are true? So is the first statement true? Second one. Second one now, right? And the third one, true or false? Perfect, right? And so to answer your question, Mariam, here, this sequence divergence is the sum of all of these divergences. You got that?
Yes, yes.
Okay, then when I get a plus b plus c, right? And I take the derivative, so this is just a function of this guy. This divergence is just a function of this guy. This divergence is just a function of this guy, right?
Yeah. So
So
that's why
it's only this term will
Gotcha.
figure when I'm going to compute the derivative of the divergence with respect to this output.
Yeah,
Make
I got
sense?
the notation. Thank you.
Right, okay. So let's continue, right? So now, so having defined so we've looked at these two models so far. Now let's go and look at our third model, which is this guy here, where you analyze an entire sequence and produce a single output. Like you look at the entire sentence and say, this is about the Steelers, right? So, or in question answering, you just look at the entire text and you say, this is what is the color of the sky, blue, red, green, right? Something of that kind. So here, again, or speech recognition, you have a sequence of inputs and you have to decide the phoneme or sentiment analysis, you name it. Now, here again, the way the model would be trained, you're going to be giving sequences of inputs and the single output that you're expecting at the end of the sequence of inputs. So when you train the model, so over here, once again, at inference time, the same thing is going to be performed. You analyze the entire sequence, and once the entire sequence has been analyzed, you're going to produce a single output. But what happens at other times? Can anybody tell me? We're looking at the output at the final input, but what about the other times? Knowing what we know about recurrent networks, are there any outputs over here or not? So here's what is happening, right? An output is still produced. We are just ignoring it, as you guys pointed out, right? We just look at the output at the final time. So now when I train the model, at the end of the input, the model produces some output. I have a desired output. I compute the divergence between the two. And this divergence can be, the derivative of this divergence can be back propagated. But in doing this, I'm missing something. I'm ignoring something that I could potentially use. What is that? Anybody want to guess? What could the hidden states? Here's what's happening. These divergences are the desired these ignored outputs, right? We are ignoring those, but say I'm performing speech recognition, right? If the input sequence represents the phoneme R at the final input, then at the previous inputs too, it's reasonable for us to assume that it continues to represent R, right? And so I could just say, you know what? I'm going to replicate this guy at each of these times. And this is the divergence I'm going to use. And what have we done over here? We've converted this to the time synchronous version all over again. Now, specifically, you can think of it as the weighted sum of these guys. And the reason we're looking at the weighted sum is that how you use this is going to be problem specific. For speech recognition, if I'm recognizing speech, then if the input represents the phoneme R over here, it also represents the phoneme R here and here. And so I'm going to just sum these three guys. On the other hand, if I'm performing something like sentiment analysis, then the sentiment is really not apparent at these times. So the weights over here are probably better off being 0. So a generalized setting is to say I'm going to take a weighted sum of, I'm going to assume outputs at all times. I'm going to compute derivatives at all, the divergences at all times, and I'm going to take a weighted sum of all of these guys. And the setting of the weights is going to depend on the problem. This makes sense? Yes or no? What about the rest of you guys? Okay, guys, give me a thumbs up so that I can see 25 thumbs up out of the 190 attendees. And I know that some fraction of the students are paying attention. Okay, thank you. So this model has been dealt with. Now let's look at this model. This model is order synchronous, but time asynchronous. But in reality, this model is just many copies of this guy, right? So Christine, over here, I would give a weight of 0 to these guys in some problems and not in others. For example, if it is sentiment analysis, or if I'm answering this question, answering color of sky, till I get to sky, I have no business saying blue, right? So in this case, I probably don't want to be considering these things. For speech recognition, if it's R over here, it continues to be R in these cases too. So here I just set a weight of 1. Did that answer your question, Christine? Right, okay. And this is what we're going to be using, guys. Okay, Mel, we're going to get to that, right? So now this is the problem you're looking at. But this problem really is just many copies of this network, except they're attached to one another. So you can think of this as this block, but another block of the same kind, and another block of the same kind. So here I have a sequence of inputs, and I have to recognize that this represents the phoneme sequence but. And so given the sequence of inputs, the inference says I must produce enter in an order synchronous but time asynchronous manner. Now, this seems to be a very simple extension of this guy, but it causes a complication. Can someone tell me what that complication might be? Anybody? What could this complication be? Anyone? The backpropagation? The model needs to know, right? How do we know when to output symbols? The model is producing outputs at every time, and we have no way of knowing which outputs to consider. That's a challenge, right? So how do we deal with this? And well, no, you're going to see this, right? That's why we're spending time on this. So how do we deal with this? First, to see how we deal with this, we have to consider that at each time, the network actually outputs a probability vector. So if you have a vocabulary of possible outputs, like if you're performing speech recognition, you'd have a set of phonemes. You're going to be computing the probability of each phoneme, a probability vector over the phonemes at each time. And so specifically, at any time, this probability vector is simply giving you the probability of the different phonemes given the entire input sequence. If it's a one-sided model, it's giving you the probability of all of these phonemes given all the input until here. If it's a two-sided model, it's giving you the probability of all of these phonemes at time 4 given the entire input. So that's what each of these vectors is. The probability, this vector is the probability that the fourth vector belongs to these phonemes, different phonemes, given the entire input sequence. So you're considering them and computing the probabilities for just the fourth vector. That's what this vector is. You're going to have one such vector at each time. Did this make sense? This figure? Okay. So give me the thumbs up, guys. Those help me, right? Okay. I see 5 thumbs up or 7 thumbs up. Okay. So now, again, any network with a softmax output is actually outputting an estimate of the a posteriori probability of the classes given the input. So at any time, you're computing the probabilities of all of these phonemes given the entire input, right? And when we perform classification, you typically just pick the class with the highest probability. And that's basically the same principle we're going to use here. Except, here's what we want to do. When I'm performing recognition, when I'm performing the sequence, generating this output sequence, I'm generating an output sequence but the number of symbols in the output sequence is lesser, or at least not more than the number of symbols in the input. And so I'm trying to find the output sequence whose length I don't know. All I know is that it's lesser than n, or at most n. And I'm going to try to find the output sequence which has the highest probability given the entire input sequence. Is this making sense? This statement here, because everything else depends on this. Yes, no, guys? Is this making sense? Okay, guys, give me the thumbs up, right? So here, Hector, I'm given the input sequence and I want to find the output sequence, right? I don't know how long the output sequence is. I could give you, for example, in speech recognition, a sequence of 100 vectors representing 1 second, but the output could be a sequence of just 4 phonemes, right? And so I want to find the output sequence that is most probable given the input sequence. Except I don't know how long that output sequence is. That makes sense? Hector, did that make sense to you? Yeah. Yeah. Okay. So, well, bear with me, Hector. So how can I do this? I can do something trivial. I can just pick the most likely symbol at each time, like so, right? And then this is greedy. Miguel, you're right. So I can just pick the most likely symbol at each time. And then I know that the output is sequence is short, so I can just merge all the intermediate guys and say all of this, I'm going to output a G when the sequence of G's ends, F when the sequence of F's ends, and so on, right? Now, and then I'm going to get 4 outputs. What could be a problem with this? Anybody? What could be a problem with this? Right? You cannot distinguish between 2 F's and a single F. This distinction vanishes. Exactly, right? So you have a problem. And so the resulting sequences could also be meaningless. Now, you can improve on this by imposing external constraints on what sequences are allowed. So you could allow only sequences corresponding to dictionary words, for instance, or you could use special separating symbols to separate repetitions. We will see this in the next class. But in any case, we have some semblance of an idea of how to generate output sequences given the input. I'm going to refer to the process of obtaining an output from the network as decoding. We'll see that, right? Now, this is in fact a suboptimal decode, which just finds the most likely time-synchronous output sequence. I'm producing one output at every time. And so the output is time-synchronous, and I'm picking the most likely time-synchronous sequence, which is not necessarily the most likely order synchronous, but time asynchronous sequence. And we'll see why this is the case, okay? But anyway, we've sort of partially addressed how to perform inference. We're going to see more of this in the next class. The more interesting question is training. How do I train? Now, let's say in my training data, I'm going to be given an input sequence and an output sequence. But so for example, I might be given the sequence of 10 vectors and be informed that the output sequence represents the phonemes b, and t. But I'm also given information about where the b occurs, where the occurs, and where the t occurs. If this information is given, then training is simple. And this business of telling me where I must output the b, where I must output the where I must output the t, this is what we call alignment. We are aligning the sequence of 3 outputs with the input. Now, if I have a sequence of 3 outputs, it can be aligned against the input in many different ways. So for example, if I have these 10 inputs, but could be aligned like so, with b coming at time x3, or at x7, and t at x9. Or like this, b at x1, or at x6, t at x9, right? The only constraint is that t always occurs at x9. And so simply knowing what the sequence of characters is doesn't tell me the alignment. because I have many alignments for the same sequence of outputs. So if I have information about the specific alignment, if I'm told, for example, that the output is bar and ter, and bar comes at 2, comes at 5, and ter comes at 9, or bar comes at 2, comes at 6, and ter comes at 9, then it's easy. All I have to do is to compute the divergences at these three places. And the sum of these three divergences is what I'm going to be minimizing. But then doing this is losing something important. What am I losing? Again, if I do this, what would I be losing, guys? These things, right? So all I can do is, what I can do is to repeat each symbol in over all of the input sequence until the previous symbol. And so now this is how I compute the divergence. And the total divergence is going to be the sum of all the local divergences. And that's what I would minimize. And of course, if I'm using the KL divergence or the cross entropy, then we know that the divergence between the desired output and the actual output is simply the negative of the log of the probability assigned to the desired output at that time by the network. This we know from our previous work. And so this divergence is simply the sum over time of the negative of the log probabilities assigned to the target symbol at each time. Is this making sense? Yes or no? Some thumbs up, guys. I only see 2. Maybe 10 would be nice. Okay, thank you. So, but the problem is that when you actually provide data for, say, speech recognition, all you're going to give is the output sequence. You're going to say, here's a recording, and this recording corresponds to the phoneme sequence for but. I'm not going to tell you where the b occurs, where the occurs, or where the t occurs. In this case, how do I compute the divergence? Clearly, I'm missing information, right? So this is the problem of training without alignment. We know how to train if the alignment is provided. The problem is the alignment is not provided. So we have a couple of solutions. One solution is I'm going to guess the alignment. I'm going to somehow look at this in the input and try to figure out where the b and t must be placed. The alternative is, say, I have no idea how this must be aligned. There are many different ways of aligning it. I'm going to consider them all. And so both of these, we will discuss both of these. So here, let's consider the first solution, guessing the alignment. Here's what we're going to do. So we can, but no, it's actually not. So here's what we're going to do. I have, in this case, I've changed my example from but to beefy. And this is an example I don't seem to be escaping from. I've had it for many years, but yeah. So let's say my input is beefy, right? The symbol sequence. Then I'm going to guess just quite arbitrarily that the first b really must come at 1. The e must come at 4. The f must come at 8, and the next second e must come at 9. This is just a completely arbitrarily assigned alignment. But once I have an alignment of this kind, I know how to train the model. And so I can train the model, but once I've trained the model, I can use the trained model to go back and re-estimate this alignment and come up with a better alignment. And I can use the improved alignment to go back and retrain the model. Is that making sense? This process? Can I see some thumbs up if I got all of you guys? So Elvin, here's the thing, right? I'm not given where these symbols occurred. So I can just take an initial guess and say b must occur at 1, e at 4, f at 8, and e at 9. Completely arbitrary. That's just my initial one. And then we'll get to that, Loria, all right? So once I come up with this completely arbitrary assignment, I can train the model, right, Alvin? Yes or no? But then if I train the model, I can use that model to go back and refine the alignment, correct? We'll see how. And then I can use, okay, Hector, here's what we're going to do, right? This is what we're going to look at. How do you re-estimate the alignment? I'm assuming that you understand that given an alignment, you can train the model. So we will focus on this guy, okay? Now, again, what is an alignment? An alignment is placing these symbols against time. And so it basically tells you which portion of the input corresponds to each of the output symbols. So here, for example, again, going back to my but example, this portion corresponds to b, this to and this to ta. Here's a different alignment, right? So there are many different ways of aligning the same sequence to the input. And in the case of each alignment, using this trick that we performed here, where we just replicate the symbols and the empty space before it, I can do the same here, and which is basically by duplicating each symbol in the strip before it. And so these are all different alignments of the same symbol sequence to the input. Is this making sense? How I can get different alignments of the same input, same sequence to the input? Right, can you give me some thumbs up, guys? Right, yeah. So I see 5 thumbs ups. Can I see 15 at least? 6, are you paying attention? 10, 12, 15, all right, thank you, all right? So here's what I'm going to do. When I replicate the symbol into the space, the resulting sequence is time synchronous. Do you see that? By replicating each symbol into the blank before it, I have now created a sequence where there's a one-to-one correspondence between the inputs and the desired outputs. So now the target sequence is as long as the input sequence with perfect correspondence. Do you see that? And so here the original sequence was 3 long, but once I align it and then I replicate things, I'm going to get a time aligned sequence, which is 10 long. So I'm going to call this time aligned sequence, which actually represents an alignment of the symbol sequence to the input as an expansion of the symbol sequence. So this guy is an expansion of this guy. Is this making sense? What I'm calling an expansion? Sorry. Can you give me some thumbs ups there, guys? 4. Be nice. Okay, 15. No, it's only 13. I need 15. All right, okay. And conversely, if somebody gave me a sequence of symbols of this kind, by eliminating repetitions, I'd end up with something of this kind. So this I'm going to call a compression of this one. Did that make sense? An expansion is expanding this to be time synchronous by repetition. A compression is removing the repetitions to give you this reduced sequence. So expansions and compressions. And so the same asynchronous compressed sequence can be expanded in many different ways, as you can see. And conversely, many different alignments can compress to the same sequence. Do you agree with the statement, these two statements? Right. Those of you giving me thumbs up, be a little more active. If I see only 4, I'm discouraged. So can I have 10? Okay, right. So now our problem is this. I'm just given this guy. And given this guy of all the possible alignments, I must find the most probable. That's what I mean. When I say I'm refining the alignment, I'm given the compressed sequence. I know the compressed sequence can be aligned against the input in many different ways. I want to find the most probable one. So here's the alignment problem. You're given a k-length compressed sequence like this beefy over here. It has S0 through Sk minus 1. and you have an n length input sequence where n is going to be greater than or equal to k, because we are looking at order synchronous outputs, right? So the outputs can be, the number of inputs has to be equal to or greater than the number of outputs. And now, if I give you, when I'm trying to give you an alignment, I'm going to Sorry, guys, we're having a thunderstorm and the power's out. So I'm working off my phone now. So where did I stop? Did uh, did you get this bit? Okay. And so again, I'll probably lose a little bit of time. I'll try to hurry up because of this now. So here's the problem. You're given the input x0 through xn minus 1, these guys. You're also given the symbol sequence. You're told that this is but, for example, and we want to find this expanded sequence. And there are many different expanded sequences corresponding to any given input sequence, right? So we want to find the expanded sequence, which is time aligned, which is most probable given the compressed sequence and the input. So this is the problem that we want to solve. We want to find the symbol sequence, time synchronous symbol sequence that is most probable given the compressed sequence and the input. Is this problem making sense? Okay, give me thumb 3. So can I get 10? Thank you. Right. So here is a pole. And let me release 3. Can you see the pole? Wait. You should be able to see it now. Okay. Oh my. The city is dark. There's a complete power outage. I'm in India. Rains for the past week. All right, 5 seconds, guys. Paying attention. We will check the poll responses. just to be sure, right? And so this is getting to be a bit. I'm not sure what happened with the poll, so I'll just ask you. First statement is all right. Thank you, guys. It just auto mutes. All right. Here's the sequence of answers, right? An order synchronous simple sequences that is shorter than the input can be aligned to the input by repeating symbols until the expanded sequence is exactly as long as the input. You agree with this? Yes or no? Just give me thumbs up. I'm running out of time, so please be prompt, right? The alignment of an order synchronous symbol sequence is a time symbol synchronous symbol sequence. Yes or no, right? You agree with this? The second statement, right? And what about the third one? The symbol sequence that is time synchronous with an output can be compressed to a shorter order synchronous input by eliminating repetitions. True or false? True, right? And so order synchronous symbol sequences that are shorter than the input are compressed symbol sequence. And the last statement, is there only one way of generating an alignment of a compressed symbol sequence to an input? Yes or no? False, right? Clearly. So here's our problem again. We want to find the alignment given the compressed sequence and the input. And again, at each time, so here is the input. Let's say I'm trying to align, say, the symbol sequence BFE to this. I've got the inputs, and at each time, the network is going to produce a prob sequence of a vector of output probabilities. So a cheap thing for me to do would be to just say, I'm going to pick the most likely symbol at each time. And let's say I really want to be generating the symbol sequence BFE. If I just pick the most likely symbol at each time, will this be an alignment of BFE? Yes or no? What do you guys think? No, right? Why not? Why not? Somebody tell me why not, right? Anyone? This R is not even B, right? So you want the first portion to be B, the second to be E, the third to be four. So you're going to have phonemes here that are not in the symbol sequence, correct? Yes or no? Right. So how do you resolve this? Any suggestions? How would you resolve this? How about I block out all the phonemes that are not in my symbol sequence? I know the symbol sequence is beefy, so it only has b, e, and f. So I just block out all the rows of the table that don't have these phonemes, correct? And so this is the same as saying I'm going to be pulling out the BR, E, and FR rows and making a separate table on the top. And I'm going to be working just off this table. Now, I'm guaranteed that every symbol I produce is part of my target sequence. In this table, if I just decode on this or on this reduced grid, we are assured that only the appropriate symbols will be hypothesized. But now if I just go ahead and just pull the most likely symbol at each time from this reduced table, is this going to be an alignment of B-phi? Yes or no? Why not? Why not? They may not be in the correct order, right? So this is B, B, B. Wrong order, right? So we want to, this doesn't assure that the decode sequence correctly expands the target symbol sequence. It's in the wrong order. You need additional constraints. So here's what I'm going to do. I know the symbol sequence I want is B-phi. So I'm going to copy the BR row of this table over on top, the E row second, the FR row third, and the E row again a second time. So E has occurred twice, so it's actually occurring twice in this table, right? So Adam, I'm assuming that this is training data. So I'm trying to align B-phi. B-phi has been given to me, right? So is the construction of this table making sense? Over here. Give me a thumbs up, guys. Everything works off this table. So I'll wait for 15 thumbs up, please. 11, 13, 14. Okay, thank you. And so now here's what I will do. This table, I'm going to work off this reduced table. And I'm going to find a path through this table. The way I will find a path, I'll start at the top left corner. And I'll keep traveling through the table. But rules I will apply is that from any node, I can, any cell, I can either walk one step directly right or one step down sideways, so which is right and down. So the only kinds of movements allowed are horizontal or diagonally down one step. And I want the final end of the path to be in this node. If I consider paths of this kind, then observe that it's going to start with repetitions of B, repetitions of E, repetitions of F, and repetitions of E. Every single path which follows this rule these rules is going to be composed of repetitions of B, E, F, and E in that order. And so it's going to be an alignment of B-phi to the input. Do you see this? Yes or no? Give me thumbs up, guys. I want to see 15 of those, please. 7. Thank you. And so this guarantees that now, if I just find paths through this, I can draw this constraint in this manner by making it a graph. From each cell, I'm going to draw an arrow either sideways or one cell down, because these are the only kinds of movements allowed when I find a path through this table. And so this collection of edges composes a graph, and any path through this graph from the top left to the bottom right is guaranteed to be an alignment of B-phi to the input. Do you see this? Yes or no? Right. Okay. So exactly. If a phoneme occurs twice, you're going to have the row repeating twice. Otherwise, you don't get the structure, right? And now the problem is, of all the paths, I want to find the path that is most probable, because I want to find the most likely alignment. But then what is the probability of a path? I'm going to assign a now these are all probability values, right? I just copied a row of probability values that the network had outputted to compose this table. So these were probabilities. So this table is a table of probabilities, which means that every cell here has a probability assigned to it. I'm going to assign a probability of 1 to each edge. So if I take any partial path through this, the probability of this path is simply going to be the product of the probabilities of the cells on the path. Is this making sense? So this one is going to be, it's Y0B is the probability assigned to the symbol B at time 0 by the network. Y1B is the probability assigned to the symbol B at time 1. Y2E is the probability assigned at time 2 to the symbol E, and so on. And so the probability of the sequence is going to be Y0B times Y1B times Y2E times Y3E times Y4F. So the path with the highest score will give the order. The problem is you'd have to compute this path score for every path through this graph, right? But then in the worst case, the number of such paths is going to be exponential, and we want to find the path with the highest probability. So how do we do this? Any suggestions? Those of you with the basically you're going to use dynamic programming, right? Not Beam, just simple dynamic programming. So here's what we're going to be doing exactly. I want to find the most probable path from source to sink. And I'm going to use a dynamic programming algorithm like the Viterbi algorithm. And this algorithm is based on a very simple principle, very, very simple principle. Here's what it is, right? Consider the best path from this node, which is Y0B, to this node in red, Y3F. Now, this Y3F node has only 2 arrows over here, only 2 arrows coming in. So it has 2 parents. A parent to a node is any node from which there's an arrow to that node. So this node has only 2 parents, right? Which means that the best path to this node must go through one of the 2 parents. Is that making sense? The best path to this node is either going to go through this node or through this node. Give me some thumbs ups, guys, please. I see 3 of them. Just be a little more proactive. Okay, so how do I find the best path? Now, assuming that I have the best path scores to all of the nodes out here, right? Then there's going to be a best path score to this guy and a best path score to this guy. So the best path node to this node is either going to be an extension of the best path to this node or an extension of the best path to this node. It cannot be an extension of the second best path because the second best path is already lost, right? So it's either going to be an extension of the best path node to this Y2E or an extension of the best path to Y2F. So how do I decide? Right here, I can look at both parents and say, what is the best path score to this node? What is the best path score to this node? And I know that if this guy's best path score is lower than this guy's best path score, then extending this one is going to result in a higher overall probability than extending this one. That makes sense? Can you give me some thumbs ups, guys? So, okay, and this is basically what we're going to be doing. So the best path from Y0B to Y3F is either an extension of the best path from Y0B to Y2E by Y3F, or an extension of the best path from Y0B to Y2F by Y3F. Alternately, I can say the best path from Y0B to Y3F is going to be the best path from Y0B to the best parent of these two, extended by Y3F. And the best parent is simply going to be the parent which has the highest best path score to that node. So is this entire algorithm making sense? I'll show this pictorially, right? But yeah. Okay, so here's what we're going to do. I'm going to be dynamically tracking the best path and the score of the best path from the source node to every node in the graph. At each node, I'm going to keep track of the best incoming parent edge and the score of the best path from the source to the node through this parent edge. So, and then eventually I'm going to compute the best path from source to sink. That's a lot of words, but let's look at it, with pictures. First, some notation. I've already introduced this notation y0 superscript b. So that is the subscript is time. The superscript is the symbol, right? So y subscript t superscript s of r is simply the probability assigned to the symbol in the rth row. Here, the third row is for, right? At time t. So this is just y3 for is going to be the probability assigned at time 3 to this symbol for. Just this notation, okay? Is this notation clear? It's got to be straightforward, nothing fancy, right? Let me just continue. And so now consider the very first time, right? At the very first time, what is the best parent to this guy? Nothing. It's the first node, right? And these guys, so what is the probability of the best path from the source to this guy? It's simply the probability of this node itself. So the best path score to symbol 0, I'm indexing 0, 1, 2, 3, right? So the best path score to symbol 0 at time 0 is simply y0 of s0, s0 being b. And the best parent over here is going to be null. For all the rest of these guys, we know that these cannot be the first node in the alignment. So the best path score to all of these guys is going to be 0. So is this initialization making sense? Thumbs ups, please. Okay. And so then I can go to the next column. What I'm going to do is to go through time. And then at each time, I'm going to go down the row. And for each node, I'm going to find the best parent. And then once I find the best parent, I'm going to store the identity of the best parent. Then I'm going to pick up the best path score to the best parent and multiply it by the probability of the current node itself to give me the best path score to the current node. This is basically what I'm going to be doing. So here, for example, not all nodes will have the same number of parents. So here, for example, this top node has only one parent. So if it has only one parent, then the best parent to this guy is this guy itself, which is 0, right? So I'm just going to be storing the best parent to this one is node 0. And the best path score to this guy is y0b times y1b. That makes sense? Did this make sense? Right? Rest of it, just keep giving me thumbs up, please. I see 6. Can I get 10? I'll wait. Okay, so then this is for the top guy, but then I can now go to the second one here. This second one, so this highlighted blue arrow over here is telling me who the best parent is in my illustration. Now I can go down to the second one. The second one has 2 parents. I pick the parent with the highest probability, best path probability. Now the best path probability for this guy is 0. So the best path probability, the best parent is this one. So over here, I'm going to store the index 0. And the best path to this node is going to be y0b times y1e. So I get both the best parent and the best path score to both of these nodes. That makes sense? Or any questions, right? And these guys, it doesn't matter. Both parents are just have 0 probability. So I'm just going to block them out because they're irrelevant, okay? But I could just use the same logic regardless of what you store here. It doesn't matter. The best path score to these nodes is going to be 0. Then I go to the next time. Once again, this node has only one parent. So the best parent is going to be this one here. And the best path score here is going to be the best path score to this node times y2b. And then the rest of the nodes, they each have two parents. For each node, I'm going to find out which parent had the highest best path score. And I'm going to store its index. And the best path to that node is going to be an extension of the path to the best parent, and the score of the best path to the node is going to be the best path score to the best parent multiplied by the node probability. So basically the best path score to the best parent multiplied by the node probability. I can do this for every node in this column. That makes sense? Is the overall logic here making sense to you guys? So I'd like to see at least 25 thumbs up over here because you're going to build on this. So please continue indicating that you did get this, right? Thank you. And then I've gone down this column. Then having computed all the nodes best path scores to all the nodes here, I can go to the next column and compute the best path scores to all the nodes here, which means that for each one of these guys, I'm going to find the best parent, store their index, and then compute the best path score to all of these. So that's because you know that the best path must start from the top left corner. So the probability that the best path starts from these three guys is 0. That makes sense? And each of these only has 0 probability parents. And so now I can compute this, the best paths and the best path scores to all of these nodes, take a step forward, do this for these nodes and these nodes and these nodes and these nodes and these nodes. And now the computation is very simple, right? Because in the way I've done the algorithm for each one of these nodes, I only the number of terms I evaluated was equal to the number of parents. And here the number of parents was 2. In the worst case, it's going to be the number of symbols on the number of rows in the table. So if I have k rows in the table, then at each time, for each of the k symbols, I'm performing k comparisons. So I get k squared computations. I do this n times. And so in k squared n computations, I can compute this entire table. And so that computation is very cheap, right? So this is Hector node. These are just the probabilities assigned to the symbols by the node, by the network. That's all, right? And now, how do I find the best alignment? I know that the final node in the alignment must be this guy. So this is already known. Now I can go back and say, what is its best parent? Then I can go to the best parent to say, what is its best parent? All of that is stored, right? And I can loop my way backwards. And when I loop my way backwards, I'm going to find the best path. This makes sense? Yes or no? And so I have found my most probable alignment given the symbol sequence and the input. Beautiful, right? And now once I found this, the rest of the algorithm is straightforward. So here's a poll. Assuming I can launch this poll. Can you guys see the poll? Okay, 10 seconds. All right, let me stop the poll here. This is what you guys thought. Going back, okay. First statement, true or false? Right. Second one, true or false? Third one, true or false? false, right? You're not doing something, you're not just picking the most probable symbol from each column of the table. So the first two are true. Viterbi alignment finds the most probable alignment for a compressed order synchronous sequence to an input. It's run on a table of probabilities constructed for the compressed sequence with one row for each symbol in the sequence, derived from the probability table generated from the output of the recurrent network. So I have some pseudocode for it. Basically, I just first create the output table and then just run the simple algorithm that I just showed you. You can check out the code on the slides, and you can do this without explicitly creating a table through indirection. Anyway, so here's where we are, right? Once the alignment is done, you're going to get the most likely alignment given the symbol sequence and the input. But that most likely alignment was computed based on probabilities that you obtained from the current model, right? So it's dependent on the current model. And now this most likely alignment is going to can now be used as your target symbol sequence. And then you can compute your divergence. And the divergence again is simply going to be the sum of the divergences at the individual times, which as we saw is simply the negative of the sum over time of the log probabilities assigned to the symbols in this target sequence by the network. And now, if I compute the gradient of this divergence or the derivative of this divergence with respect to, so this is not really the gradient, it's the derivative. But if I compute the derivative of this divergence with respect to the output of the network at time t, then that is simply the it's got a bunch of zeros, and the only term that's active is going to be the term corresponding to the target sequence symbol at time t, and it's going to be -1 over the probability assigned to the target symbol at time t by the network. This is just the standard derivative formula that we had earlier. Observe that the derivative of this divergence at any time is simply dependent only on the probability assigned to the target symbol at that time by the network. And the target symbol itself is the symbol on the best path. Is this making sense? Yes or no? Okay. And so this is what we will do. I'm going to initialize my alignments. I'm going to train my models given my alignments and use those alignments to use that model to realign my data. So what we know is that the new alignments are more probable than the initial alignments because we were always finding the most probable alignment. But then once I get these alignments, when I go back and train the model, because the model itself is maximizing the likelihood of these alignments, the new model is going to assign even greater probability to these alignments. But then I can use this model and find newer alignments. And so each step of this loop is guaranteed to increase the overall probability assigned to the symbol sequence, or alternately, to decrease the negative log likelihood of the symbol sequence as computed by the network. So is this process making sense? Each of these is locally optimal. So you're just, there are two things over here, the model and the alignment. We are fixing the model and finding the most likely alignment. We're fixing the alignment and finding the most likely model. So this loop is going to keep increasing the probability of the data, or alternately, decreasing the negative log likelihood of the data. This making sense? Give me some thumbs up, guys. Can I get 25 of the thumbs ups, please? I have 21, 22. Guys, I didn't get 25 thumbs up. I will wait. Can you give me 25 thumbs ups, please? Okay, 25. Thank you, right? And so this is the overall training model approach, where we guess the alignment. We are given the symbol sequence. You're going to use the symbol sequence to guess the alignment, and then use the alignment to train the model again. And then you're going to guess the alignment and keep repeating the process till it converges. So if you wanted to implement it, that's right, Elvis, right? If you want to implement it, you could do this either in batch mode, where you just first realign your data, your entire training data, and then update your model. Or you could perform the alignment and update the model for each instance within a batch. That would be the SGD or mini batch version. So there are multiple ways of implementing this. But then, as Elvis just mentioned, this will really work. And if you have enough data, it's going to give you a very decent model that's going to be efficient. Except that, the approach is very heavily dependent on the initial alignment that you guessed. If you guessed it wrong, then your model is going to quickly go into a poor local minimum. So this is because at each step, you're guessing a unique alignment. Here's a different way of doing it. We don't commit to an alignment during any pass. We can instead just consider all possible alignments. And this is what we call the CTC training framework. And we're also going to look at, and that we will cover in the next class. We'll also look at the issue of repetitions and how repetitions can be dealt with. So that's the end of today's class. Fortunately, over in time, in spite of the interruptions, I have some time for a few questions. Was this clear? Did all of this make sense to you guys? Any questions? If there are no questions, we will stop the recording.